This is section 3.2, approximating tangent lines. These types of problems are not going to be given an exact equation or a function to work with. You're going to be given a data or a table of values, and you have to approximate tangent lines and derivatives with a table of values. And something that comes up a lot is called the mean value theorem. So I'll give you a moment to pause it, copy this into your notes, and I'll explain what this really means. This is an existence theorem in the sense that it doesn't tell you how to find a certain value. It just says that something has to exist. And what this means is that if you have an interval a to b, so I'll just generically draw some value a and here's some other value down the road, b. And it says that if you were to connect these 2 points, so let's say a has a value up here and b has a value down over here, and f of b minus f of a all over b minus a is just finding the slope that connects these 2 points. So let me try to draw this accurately. So this line that connects these two, it says that somewhere in between, so some c value in between, is going to have the exact same slope as this. So if this is, let's say, what the curve actually looks like, then somewhere along the lines, this tangent line is going to have this exact same slope. So my tangent line, so C would be somewhere in between. So C might be over here, and this tangent line is going to have the exact same slope as this line connecting them. And that's all that's saying, somewhere in between. And we'll go over an example to see how maybe this is used. For the first example, and there's only one example in this video, deals with the table of values that describes the velocity of a rocket. So I'll give you a moment to pause it, and yes, you do have to copy this down, this table, into your notes. For part A, it wants us to approximate the value of acceleration at 43. And the way you find acceleration at 43, well, acceleration to velocity, that would be the first derivative. So I'm going to find the first derivative of velocity at 43. But notice 43 isn't listed on here. It skips over, it only goes by 10. So we have to go back to the initial definition of what a derivative was, and that's basically finding the slope. So I have to find the slope of where 43 would be. 43 is in between 40 and 50. So I'm going to find the slope that connects 40 and 50, and that's what I'm going to do to approximate it. So I'm going to have x1 and x2, y1, y2. So my slope's going to be the same way you did it in Algebra 1 and Algebra 2, is y2 minus y1, so 44 minus 40, and then x2 minus x1. And I reduce this becomes out to be 4 over 10, which is 2 over 5. So I could say that my acceleration at 43, oops, I don't know why I wrote 44, 43 is approximately 2 over 5. As far as the units, they want us to indicate the units. This is feet per second squared for acceleration, and that's my answer. Alright, moving on to part B. Must there be at least one instance where the acceleration is equal to a half on the interval 30 to 40? Give a reason for your answer. So this is where we have to kind of use the mean value theorem to show that there's going to be some point between 30 and 40 at which the derivative is equal to a half. For these, I like to kind of just draw what the data is kind of looking like. So it's talking about between 30 and 40. So I'm going to draw maybe where 30 and 40 are. So here's 30, down the road is 40. So 30 and 40, see the value of 30 is 35, so let's say 35 is right here, and then 40 is a little bit higher than this way. So it's kind of like saying that if you were to connect these 2 points and find this slope, and let's say the true function maybe goes up like this, it's saying is there some instance at which the tangent line is going to be parallel to that? Well, let's go ahead and find, what we're finding is going to find the slope of this pink line that connects them. So the slope that goes through them. Let's see, the slope's going to be between 30 and 40. It's going to be the same way, y2 minus y1, x2 minus x1. It's going to be 40 minus 35, and then 40 minus 30, which gives me 5 over 10, which is in fact 1/2. So there's going to be some instance at which the acceleration is going to equal 1/2, and then to give a reason for your answer by the mean value theorem. There will be an instance. This is basically saying we found the slope of the pink line that connects them, which is 1/2. So somewhere along the lines, the tangent line is going to have the same slope in between 30 and 40. Alright, moving on to part C. I want to use a tangent line equation to the velocity at 60 to approximate the velocity at 70. There's really two things I have to do. The first thing is going to find my tangent line equation, and then I want to use my tangent line to approximate the velocity at 70. So first thing I want to do is create my tangent line equation at t is equal to 60. So the first thing I need to do is create the point. So I know the velocity at 60 is 47. So 60 comma 47. Next thing I need to do is find my slope. The way I can approximate my slope is by using the y2 minus y1. So my slope is going to be 47 minus 44 all over 60 minus 50. So this reduces out to be 3 over 10. So then my tangent line, I have to find my y-intercept, so this is going to be 47 is equal to 3 over 10. The x-coordinate I'm using is 60, and it's going to be plus b. This is going to be 47. This is 18 plus b. And then if I subtract away from 47, if I subtract away 18, let's see, 47 plus 18 is 29. So that's my y-intercept. So my tangent line equation is going to be y equal to 3 over 10x plus 29. I want to use this tangent line now to approximate the velocity at 70. So basically I want to plug in 70 into this. So this is going to be a y of 70. It's going to be 3 over 10 times 70 plus 29. And that's going to give me 21 plus 29, which is going to give me 50. Let's see. 21 plus 29 is in fact 50. So using my approximation, I can say that the velocity at 70 is approximately going to be 50, and this is measured in feet per second. There's no you try video. There's no problems I want you guys to try on your own, because as you can see, just one problem took close to 6 or 7 minutes or so. In class we'll go over some examples, and I'll have a little handout for you guys to work through these. But the math isn't really hard. It's just conceptually, making sure that you have all the right justification and as far as what you're using and when you're using it. And that's it for this video.